Alright, coming back to this problem. So basically, it's a multi-step problem. The main thing we need to do is consider, so we have a box that's going to move down the slope and then hit another box. The first thing we need to solve for is what speed is the box traveling at when it strikes the other box. So it's going to come down here and strike this box. We can use conservation of energy. The energy before has to stay constant, so it'll be equal to the final energy down below. So initial energy has to equal final energy. Solving that, we end up, so the initial energy was mass 1 times G times R. There's no kinetic energy, so this is just the first box. And that's equal to, once it's down at the bottom, it's moving at some velocity. And I'll call that velocity V1. This is M1, M1. And it's going to strike another box. And so thus it only has potential energy here. And down here it's all kinetic energy. So mass, so mgh. And remember, it's a semi-spherical bowl, so the radius is r. The radius is r everywhere on a circle. That's the definition of a circle. And that's equal to 1/2 m1 v1 squared. And solving for v1, we get that the final velocity is equal to the square root of 2gr. The next thing we have to do is consider what happens when a collision occurs. When the first box strikes the second box,
Miss Bambi, come out of the office, please. Miss Bambi, come out of the office.
they move together, or stick, and thus their masses combine. They will move at a new speed in order to maintain momentum. Move together at a new speed. In order to maintain momentum. So, using momentum, we have mass m1 times v1. So, at the very beginning, so this is the scenario where the box is about to strike the second box, m2, m1. And then afterwards, they're stuck together and they're moving at some new speed. v2. So m1 times v1 has to equal m1 plus m2 times v2. And we can solve for the new speed. The new speed is thus v2 is equal to m1 v1 divided by M1 plus M2. Lastly, they're going to move together up the slope, converting the kinetic energy into potential energy. So we're at this scenario where they're moving up the slope. They're moving with some v2 speed, and eventually they will reach some high point. And this high point here is the h we're solving for. So conservation of energy. We know that the initial, so down and below is only kinetic energy, and up here is only potential energy. So 1/2 mv squared. Since they're together, it's going to be the total masses, m1 plus m2 times the velocity squared, and that'll equal their potential energy, m1 plus m2 times g times h. Solving, we get h equal to v2 over 2g, and the v2 is squared. And that's where we left off last time. Now all we have to do is clean up or resubstitute these in. So plugging 1 into 2, we get v2 is equal to m1 times the square root of 2gr. This is the v1 over m1 plus m2. And then plugging this into equation 3, h is equal to m1, the square root of 2gr, divided by m1 plus m2. This is our v2, and that's all squared over 2g. We can simplify this, and let me write it cleaner over here. So m1, the square root of 2gr, divided by m1 plus m2, all that squared. Divide by 2 is the same thing as multiplying by 1 over 2g, and that's equal to h. We can clean this up slightly. So, do you know how to distribute this to? So if we have something like a times b over c plus d all squared. The first rule, so if we have a times b divided by c like this, and this is squared, this square is distributed to everything that's being multiplied or divided together. So that's a squared times b squared divided by c squared. That's algebra. Thus, we can simplify this as a squared times b squared divided by c plus d squared. Note the square does not distribute when there's a plus sign in it. That has to be broken up by FOILing. So distributing this would be mass 1 squared. Square root squared cancels out, giving us 2gr divided by m1 plus m2 squared. And this is times by 1 over 2g. So all I did was distribute this square. Because it's m1 times this being multiplied, it distributes like that. If you had something like this, a times b plus c, and you square this whole thing, again, anything being multiplied gets the square, so that becomes a squared times b plus c squared. If we had something like this, a times b plus c squared, you can't simplify this without FOILing it out. This square does not distribute because there's a plus sign, only whenever there's multiplications. So this 2 and this g cancel each other out. And so I'm left with m1 squared times r divided by m1 plus m2 squared. And this could be an acceptable final answer. However, we are also told from the problem that they're equal masses. We are told the boxes are equal masses. So I'll let m1 equal m2 and equal to some m. So we get h is equal to m squared times r divided by m plus m squared. This is equal to m squared times r over 2m squared. Distributing the 2 to everything inside that's multiplied, that'd be 4 times m squared. M squareds cancel out. And the answer is 1/4 of the radius. And this would be the true final answer, given that the masses are equal. So if we had equal masses, note that the total height actually doesn't depend on the mass at all, as long as they're both equal. It's because everything accelerates down at the same speed. Let's do another problem. A 10-gram bullet is fired into a 4-kilogram wooden block sitting on a horizontal frictionless surface. The block with the bullet slide toward the frictionless 30-degree incline. The block with the bullet slides 12 meters up the incline. How fast was the bullet moving when it collided with the block? Do you know how to solve this?
I know how to solve the height.
How do you solve the height?
12 sin 30 or sine 30.
So sine of theta is equal to opposite over hypotenuse. So opposite is hypotenuse times sine. So we can do that. So doing that, let's see. Sine of 30? What is sine of 30? That's like the only one I truly have memorized. It's a half. It's like the only one that's like a very perfect number besides sine of 0 and sine of 90 degrees. So that's a half times 12, so this is 6 meters. So 12 meters times sine of 30 degrees is equal to 6 meters. All right, so we have the total height. So how will we solve this? This is just like the previous problem. So we have two scenarios. Whenever the objects are moving, we can use conservation of energy. Whenever there's a collision, conservation of momentum. So initially, we have a bullet striking a box. So let me draw this out. We have a bullet moving at some velocity v. It has a mass mb, and it's hitting a block that isn't moving, so no momentum here. And we have the only momentum is in the bullet. After they collide, they stick together and move at some new velocity. I'll call it v2, and I'll call this v1. So the momentum beforehand is the mass of the bullet times its initial velocity. And that's going to equal mass of the block, which they use capital M, plus, I'll actually remove the B. Capital M and lowercase m. So this is capital M, the bullet is lowercase m, and times the final velocity here. We can solve for the final velocity. The final velocity of the bullet and the block is equal to the mass of the bullet times the initial velocity of the bullet divided by the total mass, which we can go ahead and solve for. So the mass of the bullet is 0.01 kilograms times its velocity, and the mass of the block is 4 kilograms plus 0.01 kilograms. Which we get a long decimal, and I don't like putting in decimals until the very end. I will make it a simple fraction. That is the velocity divided by 401. So the initial velocity. So the bullet slows down by the speed slows down by a factor of 401 when it enters the block. Then they move up the slide. This is just like the roller coaster problems. We have some mass that has some kinetic energy, as it moves up and up and up the slide or incline, it's going to lose its kinetic energy and it's all going to go into potential energy. So the question is, what is the height, or usually we do, what is the height whenever the kinetic energy is 0 and it's all in potential? So down below, we have only the kinetic energy. That's going to have to equal the potential energy at the end. So, and I'm calling this V2, and it's going to have 0 here. So we have the mass of, so we have 1/2 times the mass of the bullet plus the mass of the block times the velocity squared. And that's going to have to equal the total mass of the bullet plus the mass of the block times acceleration due to gravity, and then times the height. Well, I have an m plus m on both sides, so that cancels out, leaving us with 1/2 v2 squared is equal to gh. Then I can solve this over here. V2 squared is equal to 2gh. And then I can take the square root. V2 is equal to the square root of 2gh. And then I can plug this into the equation. So substitute this in here. That is V1 over 401 is equal to the square root of 2gh. So V1 is equal to 401 times the square root of 2gh. And we can plug in values. We'll use g is equal to 9.8 or 9.81. Height we calculated as 6 meters. So that's equal to 401, the square root of 2, times 9.8, times 6. And that's equal to 4,348.586 meters per second. Very fast moving bullet. Seems a little high.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections, good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections,
I'll post this video
Welcome
too.
to iLectureOnline, and as I promised, here's another example of how to deal with momentum and energy in the same problem. So we have a 10-gram bullet, which is fired into a 4-kilogram wooden block sitting on a horizontal frictionless surface. The block with the bullet slide towards, so that would be after the collision, of course, and also assuming that the bullet stays stuck in the block. So the bullet in the block slide towards the frictionless.
Let's see what answer he gets. Make sure I did it right.
Since there's a collision, we're going to use conservation of momentum for this part of the problem. Then, as soon as the bullet and the block are moving to the right on a horizontal frictionless surface, and then up an incline, eventually stopping, this situation here, we have what we call conservation of energy.
So I'll post his video too, if you want to watch how he solves it. He might do things differently than me. He also shows the zeros The fact that this block was moving at 0 meters per second. Just keep in mind one thing. He uses V naught instead of V initial, which this is the correct notation you'll use, but I switched it for IPC and I'm trying to keep all my classes consistent. All right. All right, let's do this. So you're stuck in a boat in the middle of a lake. Luckily, you brought a physics book with you. And you decided to use it to propel yourself back to the shore. You throw the 1 kilogram book overboard with a speed of 10 meters per second to propel yourself back toward the shore. Assume the combined mass of you and the boat is 100 kilograms. Question is, how long will it take you to reach the shore after throwing the book? Ignore friction between the water and the boat. The shore is 60 meters away. To make this more realistic, instead of being in water, because water has so much friction, this is unrealistic. Imagine that you're on the International Space Station, you're an astronaut, and your rope gets cut. And you notice yourself, so International Space Station, you notice yourself 60 meters away from the hatch. And you have a bag of tools. And the bag of tools only weigh 1 kilogram, 2.2 pounds. If you're floating in outer space, there's nothing for you to push on. If you're in a lake, you can paddle, you can push on the water. Newton's third law, equal and opposite reaction. As you push on the water, water pushes back on you, propelling you forward. If you're in outer space, there's nothing you can push on. However, if you have a can of gas, a fire extinguisher, if you spray the fire extinguisher, some of the gas is going to go in some direction, and it has mass. So as the mass moves with some velocity out of the fire extinguisher, conservation of momentum tells you that the momentum has to be conserved. If you have the gas, if you're giving momentum to the gas, that means there has to be equal momentum in you to cancel it out. So if you're spraying the gas in one direction, you'll start moving in the other one to cancel it out. The total momentum stays constant. And, or if you throw something, if you're in outer space floating around and you were to throw something, throw a wrench, and this is something astronauts really have to pay attention to, because if they push really hard against the ISS, they will fly far back and the ISS will go off course slightly. How they actually move around is they really do have basically fire extinguishers on them. They have little tiny jet packs, and all the jet pack is just gas. They're just sending out gas, and you can measure how much gas is being leaving at some speed, and you can make yourself move around. So the first thing you need to do, so at the very beginning, you and the physics book are not moving. So your total momentum is 0 kilograms times meters per second. And this is constant. the total momentum will stay 0. After you throw the momentum, so after you throw the momentum, I throw the book. The book is going to be moving at 10 meters per second, and you are going to be moving at some velocity. We also include the boat in the equation, so let me do that. The total mass of you and the boat is 100 kilograms. Total mass of the book is 1 kilogram. So the total momentum is going to have to add up to be 0. So 0 kilograms times meters per second has to equal... here I'm going to go ahead and plug in the direction. So mass M1... it'll be 100 kilograms. I'm going to go ahead and plug in the negative V. Note, this means that I'm going to get a scalar. My velocity won't include a direction. And then I'm going to add the book. My pen's out of ink. So that would be 1 kilogram times 10 meters per second. So that is negative 100 V plus 10. Moving this over, that's 100 V is equal to 10. And then solving for it, I get a velocity of 0.1 meters per second. Right, you follow? How will you solve for the time it takes you to reach the shore? You're doing really badly this first week of ACT. You can't tell me anything. What is speed? What is velocity? What's the most simplest definition of velocity or speed? Like think elementary. How fast you're going, which is speed is equal to... This is like elementary. How do you figure out how do you figure out if you go from here to here? What do you do? Like if you go from here to Lufkin, how would you figure out your speed, your average speed? You would do what? You would multiply or divide what numbers? Your total or distance over. What is miles per hour? Miles per hour. Yes, speed is equal to distance over time. This technically we should say average speed, or whenever speed is constant, which it is. We assume there's no friction and your speed isn't changing. So we can use this simplified equation. Your velocity is equal to your displacement over time. So time is equal to your distance over your velocity. So that'd be 60 meters over 0.4 meters per second. And that's equal to 600 seconds. Or 10 minutes. Hello? All right. Part 2. 10 kilograms of rainwater is accumulated at the bottom of your boat. What is your speed now? So how would you solve this?
You would have to add the 10 kilograms to the weight that would be in the boat.
And then, so this would be conservation of momentum. So we start off with your mass times your velocity. And this is your total momentum. So now we're only looking at the situation where your boat and you are moving. You're moving at 0.1 meters per second, and you have a total mass of 100 kilograms. Momentum does not change, so this must be equal to mass plus 10 kilograms times a new velocity. Thus, your velocity is now going to be your original momentum, so mass times velocity, divided by your new mass. So mass was 100 kilograms, moving at 0.1 meters per second, divided by 110 kilograms. Which is equal to 0.0909, and it's repeating. Basically 1/11th. So you went from a tenth to 11th, or 0.1 to 0.09 repeating. This also, so let's do a few more examples. Let's suppose you have a shopping cart. Its mass is, let's say, 2 kilograms. And it's moving at 10 meters per second. Let's suppose, as it's, so someone pushes a shopping cart through a shopping center very fast. And then all of a sudden, someone chunks in a ham that weighs 5 kilograms into it. What would its new speed be? Let's say they just drop it in. So they're not giving it any horizontal velocity, they're just dropping it straight down into it. The momentum beforehand would be 2 kilograms times 10 meters per second. And that has to equal to 5 kilograms plus 2 kilograms times the new speed. So that's 20 kilogram meters per second divided by 7 kilograms as equal your new speed. So the cart was originally moving at 10 meters per second. It will slow down to 2.857 meters per second. Have we done impulse yet? Didn't on a test, did I have a little test where where I said a car driving through a wall versus a Bay of Hell? I mean, not Hell, Bay of, hey. I don't think so. This would be Impulse. So we look at the cheat sheet thing I gave you. We have a concept known as impulse. It has the exact same units as momentum. If you remember the kinetic energy and work, remember how work and energy have the same units? That's because work can be defined as the change in kinetic energy. Impulse can be defined as the change in momentum. I believe that's correct. Let's see. No, it's not. Never mind. Yeah, it is. Yeah, it is. There's two equations. So remember when we did work, we can define it as F times D, or we could define it as the change in kinetic energy. I'm going to introduce a new concept known as the impulse. What do you think impulse is?
Well, you said it was a form for the changing momentum.
But if you gave something an impulse, what do you think that means? Have you ever heard that term?
Well, like, sometimes in video games, it's like, this impulse grenade, it like shoots you across the map.
Alright, so, you've more likely seen it in video games, especially impulse grenades. There's something you've probably seen in scientific movies, especially with rockets and spaceships. Like an impulse drive or impulse. Basically, it's a force over time. So we let the letter J represent impulse. And it's equal to force times time. Work is force times distance. Impulse is force times time. And force times time. So the change in force times time is equal to let me actually rewrite this. So normally time is an interval. Usually, I've been writing T, technically it's delta T. So if I do force times delta T, that is equal to the change in momentum. If you look at your formula sheet, it shows F times delta T. So I think it would be appropriate just to do Ft is equal to delta P. Make it simpler. Which means impulse is also equal to the change in momentum. So this concept, so delta is what we use in high school level. It means change in. To be more precise, it's derivative. We want to use instead, which is way more advanced. But showing you little things you can do with delta, this works for any single thing. So if I take the delta of mass times velocity, and mass is constant, you can pull that out. And it becomes delta V. So mass times change in velocity. The reason this works, so we have mass times velocity 1 minus mass times velocity 2, or minus mass times velocity 2. You can factor out the mass. Right? So this is an important concept. So change in momentum gives us a way of calculating force. So this reconnects it back into force. For example, so if your momentum is, so let's say that you start out going 60 miles per hour and you slow down to 0 miles per hour in your car. So you have some momentum and then you go to 0 momentum. Now, if you do this over 10 seconds, what would your force be? Not that much. And you feel yourself to go forward, definitely. There's somewhat slamming on the brakes. You're going from 60 to 0 in over 10 seconds. Now imagine you go 0 miles per hour, 60 miles an hour to 0 miles per hour in half a second. You slam into a brick wall. How much force do you think is involved into slamming into a brick wall versus just normally slamming over a brake over 10 seconds? So as your time goes down, your force has to go down. Your force has to increase to compensate for it. In this case, it's a factor of 20. This uses 20 times less force than this scenario. So, and this concept is known as, so your impulse. Your impulse would stay constant in this scenario. So in this scenario, we're only looking at initial and final. Since we're going from 60 to 0, that means J is constant in both of these, or J is the same. Your starting momentum and your final momentum is the same. But this allows us to imagine force and time